carbon cycle on Earth is amazing. You never would have believed it if you hadn't seen it for yourself. There's this uncanny stability. The climate of the Earth is very stable through geologic time, even though the sun has been getting warmer through time. And there are other aspects, too, of the carbon cycle, like the oxygen concentration of the atmosphere, which has this incredible stability. So we're going to think of the carbon cycle as a series of these three reservoirs of carbon, each of which exchange CO2 with the atmosphere. So the atmosphere is kind of like the grand central station of the carbon cycle. It's the smallest of these reservoirs, but it's the way that carbon goes from one reservoir to another. So in this lecture, we're going to focus on the solid Earth as it affects the atmosphere, because this sort of sets the stage for why the three terrestrial planets, Earth, Venus, and Mars, are the way they are. So exchange of CO2, of carbon between the solid Earth and the atmosphere is governed by a chemical reaction called the Urey reaction. So on this side, we have a very simple chemical formula for an igneous rock. So this is a kind of a rock that froze from lava or from magma, which is what they call lava if it's underground, a crystalline rock. Calcium, silica, O3. And here's carbon dioxide. And on the other side of the reaction, we have calcium carbonate, which is limestone, and SiO2. These are the two main components of sedimentary rocks. So like all chemical reactions, there is an equilibrium, a state of lowest energy. And this particular reaction, because it has a gas, one of the chemicals is a gas, it has a very strong temperature dependence. So if you take a bunch of these elements and put them together at very high temperature, it favors this side of the chemical reaction. It wants the carbon to be free as a gas if it's hot. The same way that water vapor, there's more water vapor if it's warm, because the free form wants to find itself in the higher temperatures. Whereas at colder temperatures, this side of the chemical reaction is favored. So this sets up a kind of a dynamic duality between the deep Earth, where it's very high temperature, which basically wants all of the carbon to be in the atmosphere, like Venus. All of Venus's carbon is in the atmosphere. There's 70 atmospheres of CO2 on Venus. It's almost more like an ocean than an atmosphere, Venus. The low temperatures at the Earth's surface would really want carbon to be in the form of calcium carbonate. So the equilibrium, according to the low temperature at the surface, would only have about 10 parts per million of CO2 in the atmosphere. Whereas the atmosphere in the natural world before the fossil fuel era was about 280 parts per million. And today it's just crossed the boundary of 400 parts per million because of human activity. So the real CO2 in the atmosphere is kind of in between what the deep Earth wants and what the shallow Earth wants. So this is a diagram that shows the basic playing field for how the deep Earth and the surface Earth try to relate to each other in deciding what the CO2 concentration of the atmosphere should be. You have this sort of a cycle of carbon that goes out from the solid Earth and then back to the solid Earth. Coming out of the solid Earth, you have CO2 degassing from volcanoes, and also the hot springs at the bottom of the ocean have a lot of dissolved carbon in them. And then the CO2 reacts with igneous rocks. Here I've written the Urey reaction in a more simple way. I've gotten rid of the SiO2 on both sides because that doesn't really, it makes CaO look more like a real rock, but it doesn't really affect the carbon cycle other than that. So just stripping it down to its essentials, we have the igneous rock here and the CO2 making the calcium carbonate. So those two reacting together to make carbonate, that's a process called weathering. And then the calcium carbonate is deposited on the bottom of the ocean, and eventually, as the ocean crust is subducted down into the Earth, the calcium carbonate gets carried down into the hot interior of the Earth, where the high temperature end says, I don't want that carbon to be as calcium carbonate anymore. I want to cook that stuff off and remake some igneous rock and release the CO2 back to the atmosphere. So this sets up a whole cycle of carbon coming out of the Earth and then going back into the Earth. Now, the rate of weathering depends on rainfall, runoff, because in order to dissolve a rock, you have to have water to dissolve it in. To a first approximation, every gallon of water that runs down off of the land to the ocean is carrying about as much dissolved rock as it can. And so the way to make this chemical reaction happen more quickly is to have more gallons of water washing over the land. And the rate of runoff from the land is a very strong function of the temperature. So the biggest river in the world is the Amazon. It's in Brazil in the tropics. Many more inches of runoff per year in the tropics than in the high latitudes. And the Earth's temperature ultimately depends on carbon dioxide. So the more carbon dioxide you have, the warmer it is, the faster you can do this weathering reaction. So this ends up being another beautiful negative feedback system, just like our kitchen sink. So we can recycle this analogy just again and again for all kinds of different things. So in this particular application of the analogy, the water coming out of the faucet into the sink is the volcanic degassing rate. That's sort of what's driving the system. And then the rate of weathering depends on the water level in the sink. The rate of water going down the drain depends on the water level in the sink. The rate of weathering depends on the amount of CO2 in the atmosphere. So what happens then is that if you have some volcanic degassing rate, some certain number of molecules of CO2 every year coming out of the Earth, and if the rate of weathering is higher than that, that means you're taking carbon dioxide out of the atmosphere faster than you're putting it in, just like if it was going down the drain faster than coming out of the faucet. And so the CO2 would tend to drop until it approached and ultimately equaled on an average, in an average way, the rate of degassing from volcanoes. Or if you started with no CO2, you'd have more coming out of the Earth than is going back into the Earth, and so the CO2 would build up until it approached this equilibrium from the other side. So this sounds really cool. It sounds as though this thermostat mechanism, this negative feedback, will clean up our global warming mess by absorbing our CO2. The trouble with that idea is this time scale, how long it takes to happen, is on the order of 1 million years. So it's not something that we can wait around for. So looking at our 3 Goldilocks planets, Venus, Earth, and Mars, Venus suffered a runaway greenhouse effect, you already know. And so the water in the oceans boiled, goes into the upper atmosphere where the ultraviolet light breaks it apart. You lose the hydrogen to space, the water's gone, that's it forever. Well, now the nail in the coffin is if you have no water, you can't have any weathering. And so you have broken the thermostat. All of the carbon gets cooked and put into the atmosphere. That's why the atmosphere of Venus has 70 bars of CO2. That's why all of Venus's carbon is in the atmosphere rather than on Earth, where almost all of our carbon is in calcium carbonate or other sedimentary rocks. On Earth, the thermostat will eventually clean up the fossil fuel CO2, but it takes a very long time. And the other thing you should know is that there are ways in which the geometry of the geology can change to sort of alter the set point of the thermostat. The thermostat regulates the temperature the way a thermostat of a house can regulate the furnace and regulate a house's temperature, but it takes a long time to get there. But you can also slowly change the dial on the thermostat by changing the geometry of where the land and ocean are, and mountain building, and how fast the CO2 is coming out of the Earth by degassing and things like that. So Earth has tended to drift back and forth between sort of hothouse climates where there's basically no ice on Earth at all, and then climates like today, we call this an ice age climate, even though it's not as big an ice age as it was 20,000 years ago, the last glacial maximum, but there still are major ice sheets on Earth in Antarctica and in Greenland, and so geologists would say that we are still in an ice age. If you go to a natural history museum and go see the dinosaur dioramas, they always look very tropical. That was, the dinosaurs existed during a sort of hothouse period of Earth's climate. And so this going back and forth between these two major kinds of climate is driven by setting the thermostat, by changing the way that the CO2 is degassing from the Earth, or the way that it's weathering, or something like that. And then Mars is a smaller planet than Venus or Earth, which meant that it cooled down more quickly. So actually, the biggest volcano in the solar system is on Mars, Olympus Mons it's called, but it's tectonically dead. The interior of Mars has cooled down enough that it doesn't do this trick of metamorphosis, cooking the calcium carbonate to push the CO2 out to the atmosphere. So the thermostat is broken on Mars because it's tectonically dead. It's broken on Venus because weathering can't happen. But on Earth, it's still functioning in a very beautiful way. The oceans are another major player in the Earth's carbon cycle, and it also exchanges carbon with the atmosphere, but on a very different rhythm, a very different time scale than that of the solid Earth. So basically, there's large amount of carbon dissolved in the ocean, much more than in the atmosphere. And some parts of the ocean are releasing CO2 to the atmosphere. So the CO2 is sort of degassing or evaporating even from the ocean. Other places, the ocean is taking up carbon dioxide, say where the water is colder, so the CO2 dissolves more readily into the water than in warm water, for example. So the back and forth fluxes of carbon between the atmosphere and the ocean are huge. They are something like 1,000 times higher than the back and forth fluxes with the solid Earth. So the unit that we use to talk about carbon, or one set of units that we use, is gigatons. So giga means billion, and ton in this case means metric ton, which is 1,000 kilograms. So a gigaton of carbon is also about 10 to the 15th grams, if you find that helpful. Or another way to think of it is all of the people on Earth probably weigh about less than a gigaton. So there's much more carbon going back and forth between the atmosphere and the ocean every year by a factor of 100 or more than the total mass of all the people on Earth. And this is much bigger than the flux to the solid Earth. So the oceans are thought to be responsible for changes in atmospheric CO2 through the glacial interglacial cycles, which are documented from records preserved in ice cores in Antarctica and Greenland. So from little bubbles of air trapped in those ice cores, we know that atmospheric CO2 concentration is generally about 280 parts per million during warm times like today, during interglacial periods. And then during cold times, like the last glacial maximum 20,000 years ago, the CO2 concentration was lower, about 200 parts per million. And there's this astonishingly good correlation between the CO2 from the ice cores and temperature estimates from those same ice cores. It makes it very clear that CO2 plays a very strong role in Earth's climate. And the timing of the ice ages is extremely well correlated with fluctuations in Earth's orbit around the sun. And in particular, what seems to matter is how bright the sunlight intensity is during the northern hemisphere summer. The northern hemisphere is what's important because that's where the ice sheets have room to form. There's more land in the northern hemisphere than in the southern hemisphere. And the summer is important because that's when you decide whether to melt last winter's snow or keep it around and start to accumulate an ice sheet. So there's this very good correlation between the orbital fluctuations and the amount of ice on Earth. And so 20, 30 years ago, that seemed like the whole story, but then they discovered that the CO2 is also going up and down as the ice sheets are going up and down. So this seems like it must be a sort of a positive feedback, that the orbit of the Earth says, let there be ice sheets, and then the carbon cycle says, okay, if you're going to have ice sheets, I'm going to pull the CO2 down and amplify that cooling from the ice sheets. And so that's what makes the ice ages global, actually, instead of just from one hemisphere or the other, is the CO2 effect. So on time scales of thousands of years and longer, the oceans seem to act like a positive feedback to the climate system. However, just today, we are releasing CO2 to the atmosphere, and so the oceans are taking up some of that CO2. And so on a time scale of decades today, the oceans are acting as a negative feedback. They're helping clean up, they're dampening, they're stabilizing Earth's climate. And so it's kind of an open question whether on time scales of 1,000 years or longer, the oceans might revert to their positive feedback role and amplify our climate excursion.